Hi, my name is Andy Wilson, and I'm a graduate student working in Todd Murphy's lab.
And I'm Henry Hung. I'm an undergraduate working at Todd Murphy's lab, and I took the class that this one is based off of last year.
So we're going to be going over constitutive laws in this demo and explaining how you at home can work along with us, and using some basic household items can test spring constants, find damping coefficients, and one other constitutive law that we'll explain in the end. So to do this, you're going to need a few basic items, and Henry's going to talk about how we set up our system here.
So for our system, we will have a spring mass system, which modeled by this diagram, spring and a mass. Now I will be using a slinky to both simulate the spring and the mass. Spring will be here, and the mass will be the bundled, taped part of the bottom part of the slinky here.
So in case you don't have a slinky at home, you can use a variety of other objects. For example, a rubber band, if you have anything from the grocery store, or even a hairband that you have lying around the house. Just hang the rubber band off of something like a table and hang something with some weight at the end of it. It could be an apple, for example, and Henry will also tell you how an apple might be useful later on in this lecture. So you can also find a variety of different types of slinkies at the store. There's a little slinky that you can also use, or any sort of spring that you have lying around the house. Anything with some elasticity, we'll try to find the spring constant for. And to do that, Henry's going to explain how you go about finding the spring constant.
Okay, as Andy said, we'll be finding the spring constant. As you've learned in class, the spring constant is modeled by this equation, F equals to Kx, where F is the force, K is the spring constant, which we're trying to find, and X is the stretched length of the spring. Now to find the spring constant, we need to find what F and X are. Now because you'll be hanging the spring off of like a table or something, F will be modeled by Newton's equation, equals to ma. As I said before, you're hanging it off, so A in this case will just be gravity, equals to mg. Now gravity is a universal constant, which will be 9.8 meters per second squared. And now in this lab, it doesn't have to be that accurate, so we can estimate g, to make math and life easier, to be about 10 meters per second squared. Now we know what g is, and we need to know what m is. Now as I said before, m is modeled by this bundled taped part of the slinky, and you can be using, like, as Andy said, an apple to be your mass. So first you have to figure out what the mass actually is to plug it in. So of course the most accurate way to find a mass is like get a scale, mass it, and just plug in the number. Of course in this demo, it doesn't have to be that accurate, and you might not have a scale on hand. So there are different ways to estimate the mass of an object. For example, one is like to cold mass it. Just hold it in your hand, like say like, this feels about, I don't know, 100 grams, 1 Newton, 1 pound, something like that. Of course that's not too accurate, especially if you're not good at it. So another way, and slightly more accurate, is to compare it to something. For example, take this apple. Now this apple weighs about 100 grams, or at least according to the internet, and you can just compare it to the slinky. Say like, oh, the slinky is about twice as much as the apple, so the slinky will be about 200 grams. Now after you mass it, you have to mass your mass, whatever's using for your force, you have to write it down. In my case, I previously massed the slinky to be about 220 grams. Now because only half of it is being used as the mass in the system, that means the mass will be about 110 grams. Or in kilograms, it will be 0.11 kilograms. Now, as a side note, it's always good to have your units constant or consistent. Like I'll be using SI units, which will be meters, seconds, and kilograms. See, now we know what F is, and we need to know what X is. To know what X is, you first have to hang your spring or whatever you're using off like a table. Now, in this case, x is the stretched length. So you have to figure out the difference between the unstretched and stretched length. Now, for this linky, the unstretched length will be like this, when it's not being, when a force is not being applied to it. Now, the stretched length will be the difference between this and when a force is applied with it. So put your force and just let it hang. It may take a while to make it stop, oscillating like this. So wait a couple moments or try to stop it. So now the stretched length will be the difference between this and this, which you should take a ruler and just measure it. Now this is approximately 26 centimeters, or to keep our units consistent, to convert into meters, to be about 0.26 meters. Now we know what F and X are, so we can figure out what K is. Now isolate K on one side to have K equals to F divided by X, or as said before, F equals to mg over X. Now we know what m is. In my case, it's 0.11 kilograms, g, 10 meters per second squared, and x, 0.26 meters. Now, of course, your values are going to be different except for g, because you're using different systems or different objects to model the systems. So now I just plug in the numbers, and I get k, or k1, to be about 4.223 newtons per meter. Now, of course, in science and engineering, it's probably better to do experiments more than once, just to make sure you're doing it correctly, as I may have made a mistake and not know it. So to do this experiment again, first you have to change the force, or in this case, change the mass, which will then change the x value. And hopefully, because we want our systems to be linear, that k will be approximately the same. Now, I did this again. Instead of bundling half of the slinky, I bundled a third. Now, I'm not going to do this now, but I'm going to show you the value I got, which I got K2 to be about 4.4 newtons per meter. So just try to do this experiment again, but of course, change the force. Now, you may say, like, your value and my values are going to be different. You say, oh, but that means it's not linear, right? Well, no, because ideally engineered systems are linear, but of course in real life things aren't ideal, like manufacturing errors, and of course the big one, in my case, measuring errors, because I estimate a lot. So that accounts for the 0.17 newtons meters difference. As long as your values are close, that pretty much says that you did it correctly. And now the spring constant is only one of many constitutive elements. And now Andy will show you more about constitutive laws.
So as we saw in Henry's demo, we already have the spring and mass parameters for our spring mass system. Now the next constitutive law that we're going to take a look at is damping. Now in our system, or whatever object you may have, there's probably some sort of damping present in the system. And to show you that, I'm just going to draw a line right down here. And we're going to take a look at what the spring does if I stretch it out at this point and just let it go. Now, as you can see, the spring is pretty quickly losing a lot of its energy and not returning back down to the point that we had drawn previously. So that should indicate that there's some loss of energy, and that is due to damping in the system. Now, as you saw in class, the damping linear damping is also called viscous damping, and we're going to be using that constitutive law to try to determine what the damping coefficient is for our spring mass system. So we're going to do a slight alteration to our setup here. We're just going to add in a damper right in parallel with the spring. Now the damping force is going to be opposite our x direction, so it's going to be pointed up, and we're going to call that FD. So now that we've set up our diagram, we can try to derive the equation that we'll need to create a simulation of the spring mass damper system as the next step. So, as you've seen in class, FD equals b times x dot. So we have our damping coefficient that's directly related to the velocity of the endpoint of our spring. Now, using this constitutive relationship, we can add to the equation that you had in Henry's part of the demo. And we're also going to be moving the slinky, so we have to take acceleration of the mass into account. So the overall equation for this is going to be mg minus kx minus bx dot equals mx double dot. Now make sure that you take a look at this equation and try to derive it for yourself using the class notes and lectures from class. And it's pretty simple. All that we're really adding is this damping term and our acceleration. So now that we have the equation, it may be clear that the damping coefficient is a little bit of a different parameter than either the mass or spring constant in terms of measuring and figuring out what it is. And that's due to the fact that we have to move the spring in order to figure out what damping is going to be. If we just let the spring sit here, we can take a look at it, we can measure the length and everything that you did in the first part of the demo to figure out the mass and spring constant. However, damping we can't figure out just by looking at a static system. We have to add some dynamics to it. So to do that, we can either stretch out the slinky or we can do some other sophisticated techniques, and we actually do some of this in our lab. It's called system identification, and we're designing different ways that you can control systems in order to figure out what their parameters are. And I'll give you a quick example with this smaller little slinky. So let's say we just had it hanging, and instead of having access, we can't go in and just pull down on the end of the slinky and watch it oscillate back and forth. Instead, we can only hold the top of it and move the top around. Now, in order to get the bottom part to move, we can either kind of oscillate the top of it, or we can give it a quick tug. You can see at some points the spring is going to start bumping into the top. So one thing that we try to do in research is figure out what the optimal way to excite the top of the slinky would be in order to figure out parameters such as damping or even the spring constant. And we do this for a lot more complex systems, but the basic idea is the same, that we're using spring, mass, damper systems, and we're trying to estimate parameters within the system. Now, for this demo, we're going to keep it real simple, and we are going to just pull on the end of the slinky. And we're going to give it some sort of energy input since we're stretching out the spring and letting it go. Now, there's no real way also to estimate it with a ruler or Apple or anything. We can't do that to estimate the damping. So we're going to use the tools of simulation to help us figure out what our damping coefficient is. So the next step of the demo is going to be using MATLAB or Python, whatever your choice is a programming language. You're going to create a simulation of the spring mass damper system using the equation of motion that we figured out here. Now, once you do that, I've created this simulation. You can create a visualization, if you'd like, of the spring. And also, we're going to plot the position of the spring over time. And this will really help us to figure out what the damping parameter is, as well as check other parameters that we've already derived. So once you have this system working, you can give it a try, and I'll let it play for a few seconds. You can see that our spring is oscillating up and down, and we have, over time, the position oscillating also with our visualization. Now, the key part of this is going to be testing out the simulation, and I'll start running it one more time. And at some point in the simulation, you're going to want to stretch your spring down and try to let it go so that it becomes in phase with the simulation. Now, if your parameters are pretty close, you should have the spring match up for a little while with your demo. And given that, you can watch how much your spring dampens out and see if it follows the trajectory that you've plotted. So what I mean by that is if you take a look at your plot of position over time, you can see that there is a definite slope here to the position. Now what this indicates is that we have put damping into the system through this damping coefficient term. Now changing what your value for B is will affect how quickly your position over time decays. So if you have a high damping coefficient, you'll see a response closer to this. And on the bottom as well, it'll match up. So if you have a higher coefficient, it'll contract much quicker. All your energy will be lost, pardon me. If you have a small damping coefficient, you won't see it level off quite as much. It'll take a long time for it to stop moving up and down. And this will really depend on what system you choose. Slinkies don't have too much damping, so you're going to have a relatively low damping value. Something like a rubber band or hair tie may have more damping. And a good test would be to see what different damping coefficients are of different systems that you can find. In this case, we found, I matched it up, and you could see in the demo it was okay. You're not going to get it perfect as any engineered system, but you can get close with the simulation. So I found that this damping coefficient was about 0.007 Newton second per meter. So depending on your system, you can figure out if that is a reasonable term, if that is too high, too low. And you can also check out your spring constant and mass parameters as well. If your spring and mass are off, you might see that your simulation is either going up and down too fast, too slow, and if your parameters are just right, it should stay pretty much in phase with your actual Slinky or spring mass damper system. So using this technique, you can try to match up simulation with a physical system to determine if your parameters are correct in estimating the physical system. Now, as the last constitutive law that I hinted to in the introduction, we're going to take a look at electrical system. Now, I know we haven't talked about electrical systems in class yet, but for those who are familiar with electricity, we're going to talk about Ohm's law. Now, we're going to discuss electricity and constitutive laws in about week 7 or 8, so you can always refer back to this if you want to and try out this demo as well. So Ohm's law is given by the equation V equals I times R. V is our voltage, I is current, and R is resistance. And to test this out, we're going to create a simple circuit. We're going to hook a battery directly to a resistor. This battery will provide the voltage across the resistor, which has a specified resistance. And once we hook it up, we're going to have current flowing through the circuit. Now, as you can see, this is a linear relationship, very much similar to the viscous damping and the spring constant system that we have found. And in a way, they're all sort of related. So to test this out, we need to measure both the voltage and current in the circuit. To do this, we're going to use 2 multimeters. Multimeters are generally a good way to measure any sort of characteristics in the circuit, and it's pretty necessary because you can't just get a ruler to measure out distance or anything like that. So we have our circuit set up, and we'll take a look at the values. And on the left is our voltage reading, and the right is the current reading. So if we write down the values here, we have 5.85 volts, and we have 1.26 milliamps. So given these two quantities, we can figure out what the resistance is of our resistor. So we'll just plug that into the equation. 5.85 volts equals 1.26 milliamps times R. And we're going to divide 5.85 by 1.26 milliamps. Make sure you divide this by 1,000 as well, because we're going to use SI units, so you want volts and amps. And the result is going to be 4,640 ohms. Now, generally, we want to reduce this to a smaller number, so we say 4.64 kilo ohms. So how do we check whether this is right? Well, fortunately, resistors have specified resistances on the resistor themselves. They're the little color bands on the resistor. You can look on the internet for how to read those. And I read this off, and the specified one is 4.7 kiloohms. And that's what the resistor is rated for. However, even in engineered systems, you'll see that there's a difference between what we'll measure and what the actual parameter is rated for. And manufacturers take that into account. There's a tolerance that's also displayed on the resistor. And this one is plus or minus 5%. So you can see that our measured value is well within that range. And therefore, our system is pretty linear in the resistance. So now we've looked at 3 different constitutive laws: the spring versus force law, the viscous damping law, and Ohm's law with electricity. You can see that these are all pretty much linear, but they are linear because we are using engineered systems. If you have given systems around the house, you may see that the numbers are off a little bit, but should be fairly close. So now, go ahead, try one of these out on your own systems, or try them all out. We're going to have a link that you can submit videos of your demos on, and you can try to either do the demo that we've shown here in this video, or feel free to go around your house, anywhere around, and try to estimate parameters of various objects. See if things are linear, see if they might not match up with the equations that we've shown here. And feel free to submit those videos to us, and we're looking forward to seeing what those are. If you need a copy of the steps to replicate this demonstration, PDF's available in the lecture notes. And please go through, try this out, and we're looking forward to seeing how you guys do. Thanks.